In this video, we're going to look at a new theorem called the mean value theorem. The mean value theorem states that a function that's continuous on a closed interval and differentiable on the open interval, then there is a value c in that interval where your tangent line will be the same as your secant line. This will make more sense if you look at this picture down here. So I drew a function f that is continuous on a to b and differentiable on a to b. And the mean value theorem states that there is some c in between a and b where the tangent line at the c is going to be the same slope as the secant line. Now, there could be more than one c values. You can have more than one tangent lines that are going to be the same as your secant line. So for example, in this picture over here, I drew a new f graph that's also continuous and differentiable from a to b. But if you take a look at the different tangent lines I have, they share the same slope as your secant line. Remember, the secant line is the slope from a to b, and the point of tangent c is the slope if you were to microscope into the values of those c's to see what the slope would be there. I know some of my drawings are kind of approximate, but in the end, the tangent line is the same as your secant line. So guaranteed, if your function is continuous from a to b, then you will find another value c where that tangent line is the same as the secant line. Now, if you don't have a differentiable function, then this MVT will not hold. So for example, in this graph, there's a cusp. And because there's a cusp in between a and b, f is not differentiable. And then f doesn't have a tangent, horizontal tangent, so it cannot have any tangent line that will be similar to a secant line. So notice that the MVT can only hold if f is continuous on that interval and differentiable. Now let's apply this MVT to an example. So we're going to look at a real life example first before we go back into looking at functions. A police helicopter observes a driver traveling 200 meters along a section of a highway at 10.4 seconds. And the speed limit of that highway is 60 kilometers per hour. Can the driver be charged with speeding? So we want to know if this driver is going to drive over 60 kilometers per hour or if it's going to stay underneath the limit. Now, the function we're thinking about is called the position function. And if you think about position, it will always be continuous. Otherwise, if you had a jump discontinuity, that means that you probably would have teleported, and that would not make sense. Not in this world, at least. So it's a continuous function. It's also a differentiable function as well. Which means that we can use the MVT. So the MVT will state that our average velocity and our instantaneous velocity will be the same. And this will have to happen within that 10.4 seconds. And this will happen at least once. Might be once, might be more than once, but we just want to know if we're traveling more than 60 kilometers per hour. So let's find the average velocity because we have an information to do that. That's distance over time. So your distance 200 meters times 10.4 seconds. We want to convert this so that we're in kilometers per hour. So if you take it physics before, this conversion would be 3,600 divided by 1,000. And this is 69.2 kilometers per hour. So we are clearly over the speed limit here. So by the MVT, our velocity will be 69.2 kilometers sometime. Within those 10.4 seconds. So yes, the driver can be charged with speeding. Okay, now let's look at a functions. Prove that the function f doesn't necessarily have a tangent line that has the same slope as a secant line on any given closed interval. Explain why this doesn't violate the MVT. Well, first of all, looking at our piecewise function, our problem point would be around x equals 1, because we may have a discontinuity there, or maybe our slope won't be the same on the left-hand side and the right-hand side, so it's not differentiable. So we need to check. So when we're looking for differentiability before, you would find the left-hand limit of the derivative, and then the right-hand limit to see if the left-hand limit and the right-hand limit to see if they are the same. So we're going to do that first to see if our slopes are the same on either side. So the derivative of f prime of x on the right side, this is the top one here. Derivative of x cubed plus 3 is 3x squared, and then we'll evaluate that, which is going to be 3. Now we'll check the other side, the left side. So now we are taking the derivative of x squared plus 3, which is 2x. Evaluate that, then our limit is 2. So your left-hand slope and your right-hand slope are not the same. Which means that f is not differentiable. And then so the MVT does not apply. So this doesn't violate the MVT because we couldn't even use it anyway. And we're not sure if there's a tangent line that's the same as the slope of the secant line because we couldn't use the MVT. So we can't exactly guarantee it. So example 3. What if we do have a differentiable and continuous function? How are we going to find this value c? If we look at our function f, this is continuous and differentiable because it's a polynomial. It's continuous everywhere. So if you want to find that value c, the first thing we need to do is find our derivative, because what we want is instantaneous. Instantaneous slope should be the same as your secant slope. Now your secant, remember, that's y2 minus y1 over x2 minus x1. We have our x values. You probably need to find your y values, which is what we should do. So we'll evaluate f of -1 and f of 1 to find those y values. F of -1, that's negative times -1 squared, negative 1 minus 2. Overall, this is 0. And if you evaluate f of 1, this is going to be -2. Now your instantaneous, your instantaneous slope, that'll be the derivative of f of x. So we want to find f prime of x. We might want to rewrite this before we take the derivative and distribute this x in the bracket. So if we take the derivative of f of x, it's going to be 2x squared minus 2x minus 2. Sorry, that's 3x squared minus 2x minus 2. Then your secant is y2 minus y1. So that's minus 2 minus 0 all over x2 minus x1. And that's going to be 1 minus -1. Now we want to simplify this and solve for that x value. I'm going to move the -1 to the other side, have everything on one side, and then we'll factor out to find our x. So once we factor this is 3x plus 1 times x minus 1. So our possible x values are 1 over 3 and 1. Now be careful before you state that these two are your final answer, because 1 is actually our end of the interval. So it can't be an endpoint by the theorem. Remember that C is a value in between A and B, but it cannot be A and B. So it's not an endpoint by the theorem. So this value, negative 1 over 3, is our only value of C. So I want you to try the next question then, and then press play for the solution. So for the try this, if you take a look at our function, it's not continuous. It's undefined at x equals 1. So we can't apply the MVT here because f is not continuous. That's it for that question. Now there is an application of MVT that's pretty useful. It's called the increase and decrease test. This tells us where our function f is increasing and decreasing without drawing pictures. We can just look at our equation of our function and determine our increase and decrease, which in return will determine our max and min. So the first thing to do to use this increase-decrease test, you're going to find critical numbers of f prime of x, and you're going to set it equal to 0. Or f prime of x where it's undefined, and then you're going to take those critical numbers that you found in 1 and make a sign diagram with them. And then you're going to read off the intervals of increase and decrease from the sign diagram. If c is a critical number, and f prime changes from positive to negative at c, this gives us a maximum, and we'll get a local minimum if f prime changes from negative to positive. So let's try an example. So the first thing we want to do, if we read back, we want to find the critical numbers. So we're going to take the derivative of f of x and then set it equal to 0 to figure out what our critical values are and when f prime of x is undefined. So the derivative of f is going to be negative 6x plus 3x squared. Now this is never going to be undefined, so we won't get critical numbers from that, but we can set this equal to 0 and then find our critical numbers that way. So in between these two terms, I can factor out a 3x. And then once I factor out this 3x, I can figure out what my x values are. So x is 0 and 2. So these are my critical numbers. Our second step is to create a sign diagram. So our sign diagram is going to include those two critical numbers of 0 and 2. And then in order to figure out if we're increasing or decreasing, I am going to plug in random numbers into our f prime of x equation to figure out if it's positive or negative. So in between negative and 0, I can plug in negative 1. And if I do that, that's a negative times a negative, which is positive. Then in between 0 and 2, I can plug in 1 back into our f prime of x. So that would be 3 times a negative number, which is negative. And then lastly, I can plug in a number that's larger than 2, which is 3, back into our f prime of x equation. So let's say 3, so that's 3 times 3 is 9, multiplied by another positive number, so this is positive. So again, you're just plugging in numbers into the f prime of x to figure out what your signs are. Now, since our interval is positive, that means our function is increasing. If it's negative, it's decreasing. Positive, increasing. So what does this mean? Well, we can determine if f is increasing or decreasing by just looking at our diagram. So f seems to be increasing whenever f prime is positive, and this happens in between negative infinity to 0 and 2 to infinity. And then f is decreasing whenever f prime is negative, and this is in between 0 and 2. So let's write all this down. So f is increasing on negative infinity to 0 and 2 to infinity. And this is because f prime is positive here. And we know that f is decreasing on 0 to 2, and that's because f prime is negative. Now we can also tell where the local max and min are, and just by looking at a sign diagram, we can kind of see the shape going on. So it looks like we have a maximum at x equals 0 and a minimum at x equals 2. So we need to evaluate f at those places to figure out our y value. So f of 0 is going to be 5, because it's 5 minus 0 plus 0, and if we find f of 2, this will give us 1. So now we just need to state our final answer. So f has a local max at 5 when x is equal to 0, and we do need to explain why. We do have it right here. This is our explanation, but we still need to write it out. So this is because f prime changes sign from positive to negative. Then we also had to state it for our local min. So our local min is at 1 when x is equal to 2, and that's because f prime changes sign from negative to positive here. And then that's it. So do the try it yourself that's just below. Try to follow the same sort of steps. So the first thing you want to do is find the derivative of f, set it equal to 0 to find those critical numbers, and also see when f prime is undefined. So go ahead and do that, and then press play when you're ready. All right, so for the first step, like I said before, you want to find the derivative of f. So you're going to evaluate this, and also using the chain rule to do that. Once you do, you're going to set it equal to 0, and f prime of x is equal to 0 when x is 0, and f prime of x is undefined when x is equal to plus or minus 3, because you'd have a 0 in the denominator. Then your next step is to use those 3 critical numbers you found and make a sign diagram. So 0, 3, negative 3, they are your critical numbers. Remember, when you're using your sign diagram, you're plugging in numbers within those intervals back into f prime, not f, but f prime. This will give you your values for decreasing and increasing for f, and I'll tell you if f primes are positive or negative there. So once you have your sign diagram, you can see the picture of it. You can tell that it's increasing whenever your f prime is positive. So it's positive in negative 3 to 0, and then from 0 to infinity. Then f prime is negative, which means f is decreasing over negative infinity to negative 3, and then 0 to 3. And that's because f prime is negative. And then if you look at our local extrema, your local max is going to be at x equals 0, and this well, I didn't use a calculator, so just left my answer as is, as negative 9 to the power 2 over 3, so this is where your max is going to be. And this is because f prime changes from positive to negative here. Then your local min is going to be at 0, and this happens when x is equal to plus or minus 3, because f prime changes sign from negative to positive here. And then that's it.